Start by thanking the organizers. This is really a fantastic conference, and I really enjoyed the talks. And what I would like to show today is a different platform for studying hydrodynamic quantum analogs that is very much different from the hydrodynamic pilot wave picture. And so we'll actually apply this platform to a specific case study. I will try to show you a hydrodynamic analog of superradiants. And later I will try to show you a surprising link that we found between this system and Bournes rule in quantum mechanics. So there's a slight change in the title compared to the abstract, so please ignore that. This is a joint work with Konstantinos Papatrifonos and with John Bush. I would like to say a few words before I start that superradiants actually was mentioned yesterday. So Matteo Lebus gave a great talk about superradiants in bipartite tunneling system. This is really a fascinating work with Andre Nashbin and John Bush and Konstantinos Papatrifonos. And I'm mentioning it specifically because the study I will show you now actually grew out of a conversation I had with Konstantinos, and he was telling me about this work. And we were brainstorming about how to maybe create some experimental realization of superradiants with fluids. So thank you for inspiring indirectly this work. Okay, so I want to start with some really, I would say, quantum trivialities. This is because I would like to emphasize our interest in Bournes rule, to which I'll connect later in this talk. So we have a quantum system. It's described by a wave function, and the wave function evolves accordingly to some linear equation, typically Schrödinger's equation. And this is true as long as we're not looking, so as long as we're not measuring the function. But then when we make a measurement, then the wave function collapses to some specific outcome, specific value. Now, the collapse itself is considered to be an instantaneous process. And the selection of the outcome is considered to be inherently random. So by the way, the collapse is, even though it's considered to be instantaneous, it's not necessarily as instantaneous. As was mentioned yesterday, it might actually take a finite amount of time, even though a very short amount of time.
Excuse me, Valerie. Sorry, you have a kind of a bar up there in your presentation.
A bar? You mean the bar from the Zoom? Can I make it disappear somehow?
Yeah. Okay. No. Yes. It
maybe like this
and worse. Okay.
Yeah.
Yeah. You place it down, and
I hope it won't bother too much.
Yeah. Okay. Sorry.
Okay. No problem. So as I said, there's this the collapse to a specific outcome is random. But we can calculate, we can say what the probability is to get a specific outcome by taking the squared modulus of the wave function. And this is, well known as Bournes rule. And an important feature of Bournes rule is that this is a postulate. So it's one of postulates of quantum mechanics. So it's not derived from any first principles. Okay, so it's really basically a good guess that works. And obviously it has no classical analogs. So the importance of Bournes rule is that it allows us to connect waves to probabilities. So it allows us to connect the calculations we're doing in quantum mechanics by solving Schrödinger's equation, for example, to actual experimental measurements that we do at the lab. So there's no connection without Bournes rule. And because the wave function evolves linearly, we know that if we have a wave function, for example, that describes two systems, one is given by psi1 and the other one by psi2, we can just linearly add them and get a new wave function that describes both systems. But really the magic happens when we take the square of this amplitude, or any nonlinear dependence of this amplitude will give us the sum of probabilities plus some interference terms. And these interference terms are crucial, really central importance in quantum mechanics, especially in quantum information technologies, because it allows us to manipulate probabilities. You can use we use these principles. In general, this is used in quantum computing, and it's important really to know that these interference terms would appear even if it wasn't if we weren't talking about Bournes rules. If we had some connection between these waves to probabilities that was not linear, so any nonlinear connection, for example, if we take the power n here instead of power 2, we'll still have the sum of probabilities plus some interference terms. There will be more complex, but we'll have these interference terms. So they are very interesting. So this is why we're interested in Bournes rule, and I'm going to come back to it later on in this talk. But I started talking about superradiants, so I want to switch to superradiants. And superradiants really was first proposed theoretically by Robert Dicke in 1954. And the system is very simple. You have a two-level system. It can be just a spin-up, spin-down system. It can be an atom that sits in a ground state. So this is the image you see here. So we have an atom, it sits in a ground state, and it absorbs a photon and gets excited to an excited state. But it doesn't want to stay in the excited state. So after a while, it will emit the photon and go back to the ground state. But the emission event is random. But what we can do is, if we illuminate the atom continuously, let's say with a laser beam, we can define a steady state as spontaneous emission rate, gamma. So, you know, the atom gets back to the ground state, immediately gets excited back to the excited state, emits a photon at some random time, but on average, we have a steady rate. So if we have two atoms in such a system, then one would expect that you would have that the two atom system will emit photons at the rate of 2 gamma. But the surprising thing, and this is what Robert Dickey showed in his paper, is that this is not really what happens. So if the two atoms are very, very close to one another, specifically if the distance between them is smaller, is much, much smaller than the wavelength of the emitted light, then what happens is that the emission rate actually scales as 4 gamma and not 2 gamma. So you get twice the rate you would expect otherwise. And if you generalize it to n atoms that are very, very close together, then the emission rate will scale as n squared. And this scaling as n squared, this is what's called superradiant. So we have this enhanced emission of radiation. This is the coherent enhanced emission of radiation. Now, when the distance between the atoms is very small, which is the case that was originally considered by Dickey, then you can actually neglect the relative phase factors of each atom, and you can model the entire system classically. You don't need quantum mechanics for it, and you can explain superradiance classically. But the really surprising thing happens if you take, let's say, again, we go back to the two atom system. If you increase the distance between the two atoms and you go to the distance which is on the order of a wavelength or several wavelengths, you can still see superradiance. You actually see more than superradiance. You see that the emission rate fluctuates as a function of distance. It actually have these sinusoidal oscillations. And it fluctuates between superradiance and subradiance. But this now cannot be explained classically, because you cannot neglect this these relative phase factors between atoms. So the quantum mechanical explanation for this problem is that when you bring the atoms together, they form an entangled, basically non-separable state. And as you move them apart, they're still behaving collectively as a single unit. So you can say that n atoms collectively absorb a single photon, even though it doesn't make much sense because the photon should be divided. You cannot divide one between n atoms, but they are all as a single unit absorb this photon and then emit it at a much higher rate. So this is the quantum mechanical explanation of the problem. Now, this is the first experimental demonstration of this quantum version of Dickey's superradiance. It was done by DeVoe and Brewer in '96. And they used a pair of trapped ions. So these are just two trapped ions as their atoms. They increased the distance between them and measured the spontaneous emission rate. And these are the experimental measurements. This is, by the way, the quantum mechanical prediction of the oscillations of the emission rate. So this was a very interesting work. And what we were interested in is, can we replicate this problem, but in a hydrodynamic analog? So can we make something that will behave like these trapped ions experiment? And we found a very interesting system that can do that. So the experimental setup is actually very similar to what we have in the pilot wave hydrodynamic system. So we have a bath filled with oil, and the bath is vertically oscillated, just like in the pilot wave case. But here, we don't have droplets walking on the surface. Instead, we have two hydrodynamic cavities in the center of our bath. And the hydrodynamic cavities are basically two wells that are overlaid by a very thin, very shallow layer of oil. So what happens is that as we drive our system, as we increase the driving acceleration, we cross the Faraday threshold, but the Faraday threshold above the cavities, because they are much, much deeper than the surroundings, is actually much lower. So what happens is that we can excite Faraday waves only within the cavities. And as we cross this threshold, Faraday waves are excited between the cavities and they're emitted into the shallow layer. And I'll show you in the next slide, they actually create a common wave field. But if we keep increasing the driving the driving acceleration, what happens is that at a certain point, we're going to cross the threshold for interfacial fracture. And at this point, Faraday waves will begin to break and emit droplets. But again, the situation is the same. This threshold is much, much lower above the cavities than it is in the surrounding medium. So what happens is that we create this situation when droplets are emitted only from the cavities. So we only have interfacial fracture above the cavities, but none in the surrounding shallow layer. And what we were interested in is to see if this underlying wave field from the Faraday waves that were excited from the cavities can somehow create coupling between the emission of droplets from the cavities. So this is what this common wave field looks like. Here you can see for a single cavity and two cavities. And as we increase the distance between the cavities, you can see that there's a significant change in the wave field. But it's important to note here that these images are taken below the interfacial breaking threshold, because once the interface begins to break and we have emission of droplets, then the wave field within each cavity is very complex. But we assumed, and I'll later show that this assumption indeed turned out to be justified, but we assumed that on average, we'll have this underlying wave field will somehow affect the connection between the two cavities. Okay, so this is on the right here, you can see the video this is a slow motion video of an actual emission event. And in a second, you'll see the left cavity emits a droplet. Here you can see a droplet detaches, and soon there will be another one. But the important thing to say here is that the emission events are random. They're absolutely random events in time. You cannot predict when a specific cavity will emit a droplet. But just like in the trapped ions experiment, we can define a spontaneous emission rate gamma. And it's a function, or we expect it to be a function of the separation distance between the two cavities. Okay. Now, if we have a single cavity that is not coupled to anything, then we can measure its steady emission rate gamma. So we call it gamma naught. And that's for a single cavity. So it means that if we have two cavities that are very, very far apart, or that are not coupled in any way, then the two cavity system should emit at a rate of 2 gamma naught. And we're interested in how do we diverge from this steady state emission. And we define the anomalous emission rate here on the bottom. So it's gamma n, and it's just the difference between the full emission rate and this uncoupled emission rate, 2 gamma naught. Okay, so we want to see if this value is 0. If it's 0, it means the two cavities are not coupled in any way. And if it's not 0, then how does it depend on D? And this is probably the most important slide of this presentation. So this is our data. And the top figure here shows you our measurements for the steady state emission rate as a function of the separation distance D. And you see that just like in the trapped ion experiment, we get these sinusoidal oscillations of our emission rate as a function of the distance. And the surprising thing is that if you try to fit this data with a simple fit, and the fit you can see it here is just some constant A times cosine squared of 2kd. Okay, a very, very simple fit. You get an excellent fit to the data, and the K is not a fitting parameter here. K is the wave number that you get if you measure the wavelength of the underlying wave field I previously mentioned. So you measure the wavelength experimentally from that wave field, plug it in, calculate the wave number, and you get a perfect fit for the data. So this suggests that obviously there's no conceivable other mechanisms that will create such oscillations in the emission rate. And by the way, the emission rate, the amplification is almost quadratic. At least in our experiment that we measured, it gets to around 80% amplification for two cavities. So quadratic would be 100% amplification, and we're about 80% amplification of the emission rate. And the second figure you can see here is just a timestamp of the emission events. So you can actually perform an FFT analysis on this data, and you can show that this is really indeed a random collection of data. There's no dominant frequency here, but even without doing any analysis, you can just look at this figure and see that there's no clear pattern here. So the emission events are really random. Okay, so I told you about superradiants, and I think I convinced you, I hope I convinced you that we established a very nice hydrodynamic analog to superradiants, and specifically to the quantum version of decay superradiants with the sinusoidal oscillations and everything. And now I want to connect it back to what I started with Bournes' rule. Because if we have these, so what we've seen is that the emission rate is a function of the wave intensity. But instead of talking about the emission rate, we can just talk about the probability of a specific emission event per unit time. So it's the same as having, it's just a different way of looking at the emission rate. So this data suggests that the probability for an emission event is a function of the intensity of the common wave field. Now, again, we don't know exactly what is the shape of the wave field within the cavity where the droplets are emitted. But we know that one reasonable assumption is that when we are very close to the interfacial breaking threshold, so within the specific parameter regime, then a reasonable expectation would be that the emission rate is a function or even proportional to the kinetic energy of the waves within the cavity. And this is just because you can think about it intuitively. If you have a very low kinetic energy, then you will emit at a very low rate. If you have a very high kinetic energy, you will emit much, much faster. You will break, the interface will break much faster. Now, what happens is that in our system, the frequency is fixed. And for a fixed frequency, the kinetic energy of the waves is just like the intensity of the waves is proportional to the amplitude of the wave field squared. So in the small parameter regime where we expect this to be really proportional to the kinetic energy, we get a statistical structure that is identical to that of Bourne's rule in quantum mechanics, which is super exciting and very, very interesting. But the more interesting thing, maybe not the more interesting, but the important thing to note is that the essential feature of Bourne's rule, which is essentially this connection between a discrete random process that cannot be predicted to some wave-like continuous probability distribution, this is the essence of Bourne's rule. This doesn't change even if the power dependence on the amplitude is not squared. So if we increase the forcing and we go out from this regime I previously mentioned, it can have some other dependence. It can have an exponential dependence. It can have a dependence to the power of 3 of the amplitude. We don't know what the dependence is, but it doesn't change the physical picture. So the physical picture and the essential features of Bourne's rule still retain in this system. And it's the first classical system that we know of, at least, that exhibits this type of behavior. So once I told you that these cavities are actually coupled, so we want to somehow quantify the correlations between the emission states between the different cavities. And one way of doing so is to define this characteristic time scale tau. So tau is just the average time that it takes for a single cavity to emit a single droplet. So we can calculate it from the steady state rate. And once we have this time interval, we can define the emission states 0, 0, 0, 1, 1, 0, and 1, 1. And they just represent 0, 0 represents the case where during the time interval tau, neither cavity emitted nothing. So nothing was emitted. 0, 1, and 1, 0 means that single cavity emitted, either the left one or the right one. And 1, 1 means that both cavities emitted a droplet during the time interval tau. And now we can run the full experiment and we can count the number of events that we had per time interval. And we can calculate this. So there are many different ways of calculating correlations. And we use a very simple way of calculating correlations between the two cavities. This is the sort of correlations people do in Bell tests. But this has nothing to do with Bell tests, okay? But we just use the same correlation. And the idea is that when we have two cavities that are very far from one another and they're not coupled, then this correlation number will actually be 0 or very, very close to 0. But in our system, what happens is that we see that the two cavities are actually very strongly anti-correlated. It means that when a single cavity emits, when one cavity emits a droplet, it tends to suppress the emission events in the other cavity, which is actually very surprising because both cavities are in a superradiant emission state. So both want to emit much, much faster. But when one emits, it actually suppresses the emission event, usually tends to suppress it, doesn't always succeed, but it tends to suppress the emission event of the other cavity. The other interesting thing to note here is that we can actually change the probability of emission. So we can change not in this system specifically, but you can easily create a system where you can change the emission rate during the experiment. You can do that, for example, by changing the depth of the cavity. So if you have a piston, and you just change the depth of the cavity in real time, it means that you're changing the probability of an emission event. But it also means that you change the wave field. And by doing that, you are changing the probability of the emission events of all the coupled cavities. So what you're doing is you're tweaking probabilities between the different cavities. And by affecting a single one, you're basically affecting all of them, all the combined system, all the coupled cavities. And the reason this is really interesting because essentially, at least on the conceptual level, this is what you do in quantum computing. So when you want to perform a quantum computation, you basically tweak probabilities until you make a measurement. And by having these interference terms, you can make a specific outcome more probable, much more probable than any other outcome. So obviously, it spikes this question of can we use this system for some sort of non-classical computing? Now, we don't know the answer to this yet. We suspect we can, but we started looking in this direction. We think there might be some potential interest there. So really, the last thing I would like to say is I would like to compare the system I just showed you to the standard pilot wave hydrodynamic system. So in the pilot wave hydrodynamics, we have a droplet that self-propels across a liquid interface by this resonant interaction with its own wave field. And it gives this really rich variety of quantum, it explains this rich variety of quantum phenomena. In our system, we have, in a way, a complementary view. So we don't have particles generating waves. We have waves that generate particles. And it's very interesting because we can set up the system in such a way that the particles, the droplets that were emitted from the cavities can actually persist on the surface. They can bounce and self-propel. And in this way, we can link the two platforms together. So we can generate particles from our system and then make them behave in accordance to the pilot wave picture. So the system that I just showed you serves as basically a new platform for exploring hydrodynamic analogs that are very, very different from the one that are, not very, but some of them are very different from the ones explored in pilot wave hydrodynamics. And it's a lot, because these are systems that exhibit this probabilistic quantum phenomena, especially one that has absorption and emission of particles associated with it. So I want to cite John that said something very nice, because if we take this picture and we compare it to, for example, Dirac C of electrons, then we're going to have a hydrodynamic analog of a hydrodynamic analog. So it's a nice notion. And really, my last slide here is I would like to maybe revisit slightly the double slit experiment, if it would be performed on this new platform that I just showed you. So in the original double slit, what we have is that we shoot photons through double slits. The photons interfere with themselves in whatever interpretation you prefer to take. And when we measure, so when we look, they hit the screen. And when we measure where a single photon hit the screen, we get this interference pattern on the screen. But the important thing to note here is that the dot, each dot on this screen doesn't represent a photon. It represents an electron that was emitted due to the photoelectric effect. So we have photodetectors on the screen, and these photodetectors detect photons by emitting an electron. Okay, so each dot here is not a photon, it's an electron that was emitted, and we say that the photon hit that spot and excited the electron, but here's an alternative view. The photon in the system is a plane wave, and a plane wave goes through double slit, through both slits, and creates this interference pattern. Now, our screen in this case would be, our photodetectors will be these hydrodynamic cavities. So we have a set of these hydrodynamic cavities. Now, what I already showed you is that the emission event of each hydrodynamic cavity is a function of the local intensity of the wave field. So the interference pattern we're going to get here is going to create an interference pattern in the emission event of the droplets in this analogy to photodetectors. So it presents this very, very different take on the double slit experiment, and it somehow takes along with it the photoelectric effect as well. So this would be a very interesting experiment to perform with this new platform. And finally, I would really like to acknowledge Fulbright Fellowship for supporting my work here, and Marie Curie's Fellowship for supporting Konstantinos's work. So thank you very much for your attention, and I will be very happy to answer any questions.